Welcome to the lecture 21 of Module 9 on metrics and built-in functions in Scilab. In this lecture, we will explore the pivotal role matrices play in Scilab programming. Matrices and built-in functions form the core of Scilab's capabilities, empowering users to perform advanced numerical computations and data manipulation with ease. This lecture covers the foundational concepts of matrices, their creation and manipulation using Scilab's extensive set of built-in functions. From defining matrices to accessing elements and performing advanced operations, this session is designed to provide a comprehensive understanding of matrix operations in Scilab. Contents of the lecture would be creating matrices in Scilab, built-in functions for matrices in Scilab, advanced matrix operations in Scilab, complex numbers, polynomials, and vectors in Scilab. The learning outcomes of this lecture. By the end of this lecture, learners will be able to define and manipulate matrices of different types in Scilab, use built-in functions to generate specific matrices and vectors, query matrix dimensions and access elements using direct indexing and a colon operator, perform advanced operations such as length computation, matrix inversion, and computation of eigenvalues, handle complex numbers, polynomials, and vectors efficiently for numerical computations, and apply Scilab's syntax and functions to real-world mathematical and engineering problems. Let's begin with the basics. In Scilab, a matrix is defined by three key characteristics: the number of rows, the number of columns, the type of data it holds, such as real, integer, boolean, or string. It is important to note that vectors are simply matrices with either one row or one column. Additionally, Scilab does not differentiate scalar variables from matrices. A scalar is treated as a matrix with one row and one column. Creating matrices in Scilab is straightforward and efficient. The syntax for defining a matrix uses square brackets, commas, and semicolons. For instance, consider the following command: A equal to, within the square brackets, 1, 2, 3, semicolon, 4, 5, 6. This creates a matrix A with 2 rows and 3 columns, as shown here. Alternatively, the same matrix can be created without commas, simply by adding spaces to separate columns, such as A equal to, within the square bracket, 1 space 2 space 3, and in the next row 4 space 5 space 6. The resulting matrix remains the same. For doing matrix-based analysis in Scilab, a lot of built-in functions are used, as discussed in the following. Scilab provides several built-in commands to create matrices based on specific criteria. Let's review some of the most commonly used ones. I, that is EYE. It generates an identity matrix. For example, capital I is equal to EYE and within the first bracket 3, 3. This creates a 3 by 3 identity matrix as shown in the next slide. Here, capital I is equal to 1, 0, 0, 0, 1, 0, and 0, 0, 1. Next built-in function that we are going to discuss is linspace. Linspace, linspace, which produces a linearly spaced vector. For example, capital V equal to linspace within the first bracket 1, 10, 5. This creates a vector of 5 linearly spaced values between 1 and 10 as V equal to 1, 3.25, 5.5, 7.75 and 10. The range from 1 to 10 being divided into 5 equally spaced numbers. The next function is ones. ONES, ones, generates a matrix filled with ones. For example, capital A equal to ones within bracket 2, 3 creates a 2 by 3 matrix of ones as shown here. The next important function in Scilab is zeros. ZEROS, zeros, creates a matrix filled with zeros. For example, Z equal to zeros within bracket 3, 2. It produces a matrix of 3 rows and 2 columns with zeros as shown here. Moving on to the next function, that is rand function. RAND, rand generates random matrices. For example, capital R equal to RAND within bracket 3, 3 produces a 3 by 3 matrix with random numbers. Here R is a matrix having random numbers. Dear learner, Scilab offers flexible syntax and various built-in functions to create and manipulate matrices efficiently. Understanding these foundational concepts is crucial as matrices are the backbone of data manipulation in Scilab. Let us now test our understanding so far by attempting some multiple choice questions. Dear learner, moving forward, we now delve into the advanced matrix operations in Scilab. In this part of the lecture, we will cover essential concepts such as creating and managing empty matrices, querying matrix dimensions, accessing and manipulating matrix elements, utilizing the colon operator for flexible subscript management. Let's begin by understanding how to work with empty matrices in Scilab. In Scilab, an empty matrix is represented by empty square brackets. It is essentially a 0 by 0 matrix. For example, A is equal to an empty square bracket. This command creates an empty matrix and outputs A equal to an empty matrix. Assigning an empty matrix to an existing variable clears its contents and frees the associated memory. For example, A equal to ones within bracket 100, 100, then A equal to empty square brackets. Here the matrix A is first defined as a 100 by 100 matrix of ones. By assigning the empty square bracket, it is reset to an empty matrix. The size function is used to query the dimensions of a matrix. It returns two outputs, NR, that is number of rows, and NC, that is number of columns. For example, A equal to 1s within bracket 2 comma 3, then within square bracket NR comma NC equal to size within bracket A. The output will be NR equal to 2 and NC equal to 3. Alternatively, the syntax size within bracket A comma SEL allows selective querying. SEL equal to 1 or within the inverted commas R returns the number of rows. SEL equal to 2 or within double quote C returns the number of columns. SEL equal to double quote within the double quote star returns the total number of elements. For example, size A comma within double quote star returns an output as an answer equal to 6. Dear learner, let us see how to access the elements of a matrix. Elements of a matrix can be accessed in several ways. Like accessing the whole matrix, simply use the variable name A. Use the syntax A within bracket 1 comma j, where I and j are the row and column indices. This is for element by element matrix accessing. For example, A equal to 1, 2, 3, semicolon, 4, 5, 6 is a matrix of 2 rows and 3 columns. As seen here, A equal to 1, 2, 3 in the first row, 4, 5, 6 in the second row. Now accessing the first row, second column element by writing A within bracket 1 comma 2 gives us the answer as 2. Elementary algebraic operations like addition and subtraction can also be performed directly on matrices of the same size. For example, A equal to 1s within bracket 2 comma 3, B equal to 2 times 1s within bracket 2 comma 3, A plus B will produce the output as shown in this slide. A equal to 1, 1, 1, all the 2 rows are 1, 1, 1. B is equal to a matrix having 2 rows, all elements are 2, 2, 2, etc. And the result of addition is 3, 3, 3 in all the places of the matrix. Here, matrix B is 2 times each element of matrix A, and the addition results into the answer as seen here. Next, we will discuss another very important operator of matrices in Scilab called colon operator. The colon operator simplifies subscript management in matrices. The basic syntax is V equal to I colon j. This creates a vector from I to j with a step of 1. For example, V equal to 2 colon 4 creates an output V equal to 2, 3, 4. Custom step. Use I colon S colon j to set a custom step size S. For example, V equal to 3 colon 2 colon 10 gives an output V equal to 3, 5, 7 and 9 with step size of 2 from 3 to 10. Negative step. Example of negative step is phi equal to 10 colon minus 2 colon 3, which produces an output v equal to 10, 8, 6 and 4, which starts at 10, takes a negative step of minus 2 and goes down to 4, accessing sub-ranges with the colon operator. The colon operator is powerful for subsetting matrices. For example, let us define a 5 by 5 matrix as shown. A equal to this 5 by 5 matrix that we can see here. Now, to access the elements in the rows 2 to 3, in columns 3 to 4, we need to write A within the bracket 2 colon 3, comma 3 colon 4. And the answer obtained will be exactly the elements in the second to third rows and third to fourth column in the matrix as seen here. Next, we will explore the length function, a versatile and fundamental concept in programming used to determine the size or extent of various data structures. The length function provides the number of characters in a string or the number of elements in an array, a list or matrix. Its behavior varies slightly depending on the type of data structure it is applied to. The general syntax for the length function is as follows. N is equal to length within bracket capital M, where M represents a matrix, string, list or other structure. And N is the integer or matrix of integers returned by the function representing the length of M. The behavior of length is determined by the type of input provided. For usual or polynomial matrices, length returns the product of rows and columns of the matrix. For example, length of the matrix 1, 2, semicolon 3, 4 equals 4. For character strings or matrices of strings, the function calculates the length of each string entry. For example, length of the string within single quote 1, 2, 3 equals 3. Let's review some examples to demonstrate the versatility of length. One matrix example, the length of 1, 2, 3, 4, 5, 6 would be a 2 by 1 matrix, so the length returns 2. A string example, length of this string hello world. This string has 11 characters, so the result is also 11. Random matrix, length of a random matrix 2, 2, 2. For a 2 by 2 by 2 array, the total elements are 8. So the output is 8. Dear learner, in this part of the lecture, we discussed that empty matrices can be used to free memory. The size function helps query matrix dimensions. Matrix elements can be accessed directly or through ranges. The colon operator streamlines subscripting and matrix manipulation. Dear learner, next we would like to explore the INV function, a fundamental tool for computing the inverse of matrices. Matrix inversion is a core concept in linear algebra with applications across numerous fields such as engineering, physics, and computer science. The INV function computes the inverse of a square matrix. If the matrix is singular or nearly singular, a warning is provided highlighting potential numerical instability. The basic syntax for the INV function is INV within bracket x, where x is a real or complex square matrix, a polynomial matrix, or a rational matrix in transfer or state space representation. Let us explore an example to understand how the INV function works in Scilab. X equal to a matrix 1, 2, semicolon 3, 4. Y is equal to INV of x. This will result into y equal to minus 2, 1, 1.5, minus 0.5. To check the correctness of the inverse, let us compute x into y. If this results into the identity matrix, then y is the correct inverse of x. In this case, x into y results into the matrix as seen here. X into y is equal to 1, 0, then 8.882 into 10 to the minus 6 and 1. Here, as you can see, the diagonal elements of the resulting matrix are 1. The other elements are either 0 or close to 0, that is extremely small value. Hence, the result obtained by computing the inverse of x, that is the matrix y, is the correct inverse of x. Let us now discuss the spec function in Scilab, which is used to compute the eigenvalues of a square matrix. Eigenvalues play a crucial role in linear algebra, signal processing, control systems, and many other fields. By the end of this session, you will understand how to use the spec function, its syntax, arguments, behavior, and practical examples. The spec function computes the spectrum of a square matrix, which consists of its eigenvalues. These eigenvalues are critical in understanding the behavior of systems, solving differential equations, and performing stability analysis. The general syntax for the spec function is E equal to SPEC spec within bracket A, where A is a square matrix, real or complex. E is a vector containing the eigenvalues of matrix A. For example, let us look at some examples, understand how spec is applied in practice. Real matrix A equal to 4, 2, semicolon 1, 3. E is equal to spec A. This computes the eigenvalues of the real matrix A as E equal to 5 plus 0 into I, 2 plus 0 into I. That is 5 and 2 are the elements, the eigenvalues. Diagonal matrix D is equal to DIAG, the matrix 1, 2, 3. E is equal to spec of D. The eigenvalues of a diagonal matrix are its diagonal entries 1, 2 and 3 only. Zero matrix Z is equal to zeros 3, 3. E is equal to spec of Z. All eigenvalues for this matrix are 0. Thus, the spec function is a robust and essential tool for computing the eigenvalues of matrices in Scilab. Whether dealing with real, complex, diagonal, or symmetric matrices, spec simplifies the process and enables you to analyze a matrix's spectrum effectively. At this juncture, let us test our understanding of the topics discussed by attempting the following multiple choice questions. Dear learner, let us now explore three fundamental elements in Scilab: complex numbers, polynomials, and vectors. These topics form the backbone of mathematical modeling, engineering computations, and scientific analysis. By the end of this session, you will understand how Scilab handles these entities, their syntax, and practical applications. Scilab provides built-in support for complex numbers, enabling operations and functions in the complex domain. Complex numbers are represented as z equal to a plus bi, where a is the real part and b is the imaginary part. Syntax and operations for creating complex numbers are shown here. z1 equal to 3 plus 4 into percentage I. z2 is equal to 5 minus 2 multiplied by percentage I. Percentage I represents the imaginary unit root over minus 1. Basic operations are done on the complex numbers as shown here. Z addition is equal to z1 plus z2. Z subtraction is equal to z1 minus z2. Z multiplication is equal to z1 into z2. Z division is equal to z1 divided by z2. Few basic complex functions used in Scilab are conjugate conj within bracket z1, that is the complex number. Real part extraction real within bracket z1, the complex number. Imaginary part extraction imag within bracket z1. Magnitude abs within bracket z1. For example, z is equal to 2 plus 3 multiplied by percentage I. DISP displays the real part by computing the real part of the complex number as REALZ. Displaying the imaginary part is done like this. Displaying the absolute value is also done in this way. Then displaying the conjugate will be DISP within bracket conjugate of Z, and we will get an output as seen. Polynomials in Scilab. Polynomials in Scilab are represented symbolically and can be used for operations such as addition, multiplication, division, and root finding. Syntax and creation of polynomials are as equal to poly within bracket 0 comma within the first quote s, which creates a symbolic variable s. Then p1 equal to s to the power 2 plus 3 into s plus 2 is one polynomial. P2 is another polynomial defined as s to the power 3 minus 2 into s plus 1. Basic operations using polynomials in Scilab. Adding the polynomials P1 and P2 is simply done as P1 plus P2. Polynomial multiplication is done as P1 into P2. Polynomial division, which returns quotient and remainder, is done by doing P1 divided by P2. Roots and evaluations of polynomials in Scilab. To find the roots of the polynomial, we need to write ROOTS, roots, and within bracket P1. To evaluate P1 at s equal to 2, we need to write HORNER, Horner, P1, 2. Vectors in Scilab. Vectors are fundamental data structures in Scilab used to represent single-dimensional arrays. They can be row vectors or column vectors. Creating vectors. A row vector can be created as v1 equal to, within the square bracket, 1, 2, 3, 4. A column vector can be created as v2 equal to 1 semicolon 2 semicolon 3 semicolon 4. Ranged vectors can be created as v3 equal to 1 semicolon 5, which creates 1, 2, 3, 4, 5. v4 equal to 1 semicolon 0.5 semicolon 3 creates 1, 1.5, 2, 2.5, 3. Basic vector operations. Basic operations like sum is done as v1 plus v1. Multiplication is done as 2 into v1. Element-wise multiplication is done as v1 dot multiplication v1. Accessing the elements. V equal to 10, 20, 30, 40. Now display v2 will give an output, that is the second element, 20. Display v dollar will output the last element of the vector, that is 40. Let us combine complex numbers, polynomials, and vectors into a single example now. Define a polynomial s equal to poly 0, s. P is equal to s to the power 2 plus 2 plus 3 into percentage I into s plus 1 minus percentage I. Define a complex vector v equal to 1 plus 2 into percentage I, comma 3 minus percentage I, comma 4 plus 4 into percentage I. Performing operations like extracting the real parts, display real v. Finding the roots of the polynomial, display roots p. The results obtained from these operations are interesting to note and understand. Scilab's capabilities for handling complex numbers, polynomials, and vectors make it an essential tool for numerical computing and mathematical modeling. These features enable efficient analysis and computation in both academic and industrial applications. Let us now attempt some multiple choice questions to test our understanding of the topics discussed. In conclusion, this lecture provided a comprehensive exploration of matrices and built-in functions in Scilab, highlighting their pivotal role in scientific computing and programming. We began with the fundamentals of creating and manipulating matrices, utilizing versatile built-in functions like zeros, ones, rand, and linspace. Advanced topics included matrix squaring, element access, the colon operator, and elementary operations, all integral for effective matrix manipulation. We delved into advanced matrix operations such as computing matrix inverses and eigenvalues using INV and spec functions, showcasing their importance in solving real-world problems. Finally, an introduction to complex numbers, polynomials, and vectors emphasized their significance in mathematical modeling and computational tasks. This foundation equips learners to harness the full potential of Scilab for matrix-based analysis and problem solving, paving the way for deeper exploration into its applications in engineering and science. Dear learner, on the successful completion of this lecture, please try to answer these questions, which will make your understanding of the topic clearer. Dear learner, here we come to the end of the lecture on matrix and built-in functions in Scilab. Please try all these commands discussed here in Scilab environment. For further reading, please refer to these resources.